In section 1.4, we're looking at measuring and classifying angles. Now, before we can do that, though, we have to define what an angle is. And we define it as two different rays with the same endpoint, which is the picture I have over here on the right. Now, if I label this, I'm just going to call it ABC for now. Now, the rays that we have there that lead from the same endpoint, we call the sides. So let's call it sides of the angle. And if we remember rays, it would be BA and BC. Now the endpoint is the vertex of the angle. So that point they both start at, we call the vertex. So notice we have a point, even though it's called an endpoint, it's where we could think of maybe the two rays start and they go off in their own direction. They're not the same ray. It doesn't say about opposite or anything. They're just two rays that share a endpoint or starting point, we'll call that, for the vertex. Okay, well, we know what an angle is. Now we have to be able to name it. And you name an angle using the 3 points that make the angle, with the one stipulation that the vertex is the middle letter. So in this diagram here, I have A is my vertex. So any angle I name in this diagram, A needs to be the middle letter. Now also, whenever we name angles, we put an angle symbol out in front, and either of these would work. So if I was going to look at the whole angle here, I could say BAD. Now if we look at BAD, A is the middle letter, it is the vertex, and that is good. And we have these rays, we could say AB and AD, that come out from that angle. Now, those are the two rays, the two sides that form the angle. Now, maybe we want to flip the order that we write it. We could call it DAB. And that's the exact same angle. So it's the same vertex, and then there's still points that are on the sides. That's D and B. Okay, let's draw a line there. Let's say we wanted to look at this angle, that top piece. Well, it still has A as a middle letter, but now B and C are the rays, the points on the rays. And we could flip it around and call it CAB. Means the same thing. Last one we have here is that bottom piece. I'd call that angle CAD or angle DAC. Either one of those works. Now, again, A is the middle letter in all of them. It should be. When you're looking at a name of an angle, let's say you're reading a problem and you see it, what I like to do is first look at the middle letter, because that middle letter tells me where the vertex is and where I need to start. Then I can see where those other 2 points are and where it matches. Sometimes if we try to read it in order, we can get confused and we can mix up the vertex. But if you remember that vertex is always the middle letter, we know where it goes. Now, one exception we have to naming it when we don't use 3 letters is if we have just one angle at a vertex. So if I called this angle over here has a vertex X and a vertex Y, I could call it angle X and angle Y. Maybe I want to compare them or do something with them. This works in cases when there's only one angle at the vertex. What do I mean by that? Well, look at our picture over on the left. If I said angle A, we don't know what angle we're talking about because there's multiple angles that use that vertex. So that's something we'll see later on, but for right now you need to get used to writing the names of the angles using the 3 points or the 3 letters. So we can name them, now we need to be able to measure them. And what we use is a protractor for whenever we measure angles. Similarly how you have the ruler postulate for measuring segments, we have the protractor postulate for measuring angles. And we have that the rays of the angle can be matched 1-to-1 with real numbers from 0 to 180. What that first tells us is that any angle measure we have is going to be between 0 and 180. We're not going to have negative angles, and we're not going to have angles for the purpose of this class that are bigger than 180. So it always has to be between there. Now then it goes on to say the measure of the angle is equal to the absolute value of the difference. This is something we also saw in segments, and what we're trying to get there is if I had different points on the protractor that I had to measure from, I could subtract that and find its value, but we say absolute value so we don't get a negative. It's always positive between 0 and 180. So let's kind of do an example here. Anytime I use a protractor, I'll likely put one of the sides on that bottom line. Now if I get rid of that first, got ahead of myself, notice I have 0 and 180 there. The 0 follows up on the outside all the way to 180. So if I set one of my sides on the left side of the protractor, I'm going to use that set of numbers. Whereas if I put it on the right side, I would use the inside set of numbers because you always want it to start at the 0. So I was saying I was going to draw an angle over it. So I put one of my rays at 0, and let's put the other one right there. So when I look at this, I have my 0, and that follows up, and that goes to the 50 degrees. And maybe I want to call this angle A, B, C. If I was going to write it, I'm going to say that the measure of angle ABC is 50 degrees. Now we have that angle symbol in front of it, but I also put that M there. That means the measure of angle A, or angle ABC, is 50 degrees. That's how we would say it. Don't say M angle ABC. It's the measure of the angle the measure of angle ABC is 50 degrees. Okay, we'll use that for whenever we look at a measurement in the degrees. We'll put the M there. Again, if we're just talking about the angle though, just the angle symbol. So, let's look at the types of angles we could have. We could measure them, but with certain groups we have of angles. And the one we start with, we could think of, is the right angle. And let's just say they're angles A. Just pick a letter. A right angle will always be 90 degrees. I could have it marked as 90 degrees and have the number there. You may also have a little box. And when we see that box, we just assume that that is 90 degrees. So, on the smaller side of that, we have an acute angle. So an acute angle is less than 90 degrees. But we have to be careful because it's going to be greater than 0. So it's something between 0 and 90 will be an acute angle. So we took that right angle, that perfect corner, and we've kind of closed it in a little bit. And we have two examples there, 50 degrees, 85 degrees. Those are acute angles. An obtuse angle is a right angle that's been opened up. So it's going to be bigger than 90. So we're going to say 90 is less than the measure of angle A is less than 180. So this one will go up to 180, but if it hits 180, we get our last one, which is a straight angle, and that's when our angle equals 180 degrees. We don't really use it too much, a straight angle. If I give you a variety of angles and ask you to identify, typically it's acute, right, or obtuse. Where the straight angle is involved is when we start solving problems with a posture that we'll get to in a minute. So, straight line, straight angle is 180 degrees. So, let's go through some examples. Measure and classify and see what we have on the protractor. So if I was to list out some angles, maybe angle AFB, and look at that on the protractor. Again, F is my vertex, it's my middle letter. And if I look here, I'm looking at this angle. So I'm going to go from 0, follow it up, and it's 60 degrees. Now I could also check to make sure that's 60 degrees because it is an acute angle, so it should be less than 90, and that fits. Why I would check that and want to be careful is what if I asked for angle EFB? Because that angle would use this direction and go to the same side of FB. But in that case, we follow the 0 to the 120. So we got to be careful with that. But that one's obtuse. It should be bigger than 90, so we can kind of recognize why the numbers would fit. All right, let's take angle BFC. BFC is this angle. Now I didn't start at 0, but I can still work through it because I'm saying 60 and 90. I need the difference between the two, and that would be 30 degrees. If I did angle BFD, right here. So I have 60, and this is 125. That's 65 degrees. between the two. So that would be a 65-degree angle. Well, let's see. Let's get some more variety here. What if we wanted 90-degree angles? What if we wanted our right angles? Hopefully you see that it's AFC and angle EFC. And then last, if we wanted our straight angle would be AFE. Now you may notice on our list of angles here, F is the middle letter on all of them because it is the vertex. If I wrote any of those angles without F as the middle letter, it wouldn't be correct. So we've got to be careful as you're naming them starting off. Also, we could have flipped the letters around. I could have said BFA, BFE, CFB, and just flipped the order. It would still be talking about the same angles. Now we get on to a postulate. Now this is very similar to the segment addition postulate we looked at in section 2. That said, you add up the parts and it's equal to the whole. So if I took a segment and broke it into parts, all those parts would add up to equal the value of the whole thing. We're doing the same idea here now, but it's with angles. So let's say I have an angle. As it says here, it says RST is my angle and P is on the interior. Okay, so I'll make a point P. I think it'd be fair to say that that point is on the inside, the interior of the angle. If I moved it to right there, it's not on the interior again. So it has to be inside. So let's just settle it right there. So if that's on the interior, then it goes on to say the measure of angle RST, which is the whole thing, this angle, equals the sum of the measures of the angle of RST and PST. That should actually be RSP. Let's fix that. RSP, which is the top piece, plus PST, which is the bottom piece. So I'm saying if I add the two pieces together, it equals the whole thing. So the first bullet point uses it in words. The second one is just saying it as an equation. So the entire total of the angle is equal to the sum of its parts. We can follow that. So let's look down at our example. I have RST as 145 degrees. I need to find RSP and PST. So you look at the problem and you probably first notice we have RSP as 2x plus 10 and PST as 4x minus 3. A key thing we have to notice, and maybe you already saw it, was the total of the two is 145. If we don't know the total, we can't solve it. So I'm going to say 145 equals 2x plus 10 plus 4x minus 3. Therefore, 145 equals 6x plus 7. I get 138 equals 6x. I divide, and I get that x is 23. Now, x is 23. I'm not done. It wants me to find the actual angles. So now I can go in and substitute in 23 into each of those values. I get 46 plus 10, or 56, for RSP. We'll write that right here, equals 56 degrees. Now let's think for a second, make things easier for us. I know the total is 145. I know one of the angles 56. If I subtract 56 from 145, I get 89 degrees. So it should make sense that that would be our other angle. If I do in fact substitute 23 in, I get 92 minus 3, which is 89 degrees. So I could even say that the measure of angle PST is 89 degrees. Now that's a way to check your answer to make sure you did it correctly. They should add up to the total. I'm not going to say you just take the 56 and subtract it from 145 and you're done. Because what if we made an arithmetic error along the way? We want to be able to check that. But they should add up. In this case, it does. So, a couple more examples. In the first one, I have KLM as a straight angle, and I need to find the two other angles. So before I'm starting to substitute values in, I'm going to write out my equation. I have the measure of angle KLM, which is the whole thing, is equal to angle KLN plus the measure of angle NLM. So what do I know? Well, KLM is a straight angle. We know a straight angle is 180 degrees. Notice it's a straight line. KLN is 10x plus 5 minus 5. And then we have 4x plus 3. If I solve, I get 180 equals 14x minus 2. That becomes 182 equals 14x. So x is 13. Now, I'm not looking for x. I'm looking to find my angles. So the measure of angle KLN is 10 times 13 minus 5. That gives me 130 minus 5, or 125 degrees. The measure of angle NLM is 4 times 13 plus 3. 4 times 13 is 52, plus 3 is 55. So I got 125 degrees and 55 degrees. We can check by looking up at our diagram. Hey, 125 and 55 add up to 180, so we know we're good. Okay, let's go over to the other side. In this one, I have EFG is the whole total of the angles. It's the big angle. That's equal to the smaller piece, EFH, plus the other piece, which is HFG. EFG, let's see, is a right angle. A right angle is 90 degrees. Then I have 2x plus 2 and x plus 1. I get 90 equals 3x plus 3. 87 equals 3x, and we get that x equals 29. Now, we're not finished. That's just our value of x. Got to be careful when you do problems like this. It's really tempting, especially if it was a multiple choice problem, just to stop there and say, 29, it shows up. But what if we're ask for specific angles? So, I am looking for EFH, and that is 2x plus 2. So 2 times 29 plus 2. I get 58 plus 2, and that's 60. And then the measure of angle HFG is x plus 1, so that's 29 plus 1 is 30 degrees. So those are each of my angle values. I could check real quick. 60 and 30 adds to 90, so I know I have my correct answer. Last thing we're going to look at here is we have two terms, congruent angles. The same idea with congruent segments. Congruent angles, two angles are congruent if they have the same measure. So I'm just going to say I have angle A and angle B here. And again, I'm just using the vertex to name it. And I can do that as long as I don't have multiple angles at that vertex. So angle A is congruent to angle B. Again, that means congruent. And that occurs if they have the same measure. If they have the same measure, I'd say the measure of A equals the measure of angle B. The top part, the congruent, is saying they're the exact same angle. The object themselves are the exact same. The bottom part with the equal is saying their measurement, whatever degrees those angles measure, are exactly the same. So if they're both 60 degrees, for example, then they're congruent. But if one of them's 60 and one of them's 61, well, they're not equal, so they're not congruent. So that's something we're going to use later on. But we need to make sure we're starting to understand that idea of congruence. Now, the other thing we have is when we mark angles congruence. We're going to put these arcs in them to say they're the same. So maybe they both have one arc, means they're the same. Maybe I could put two arcs in them, means those angles are the same. If I drew some other arcs, other angles, and I want to say those were congruent. Instead of the arcs, I could put an arc and then a tack mark. That would also indicate they're the same. So as long as they have the same markings, we're just going to say they're congruent angles. Now the last part we have is an angle bisector. And this is a ray that divides the angle into two angles that are congruent. So I have a ray here. Let's label out here, A, B, C, and we'll say our ray, make it BD is our ray. So let's say we have an angle and we take array BD and it cuts in half into two congruent angles. So we're going to put our congruent markings there. So because that cuts two angles in two, cuts the angle into two congruent parts, I can say that angle ABD is congruent to angle CBD. I could also say their measures are equal. Because again, if they're congruent angles, equal measures. And let's think of a couple examples real quick. So if that's 30, and they're congruent, I know the other one's 30. If I have 44, I know this is 44, but I also know the total would be 88. I could add them together or just double one of them. Okay, with that thought, what if I knew the whole thing was 110? Then I would know each angle would be equal, and half of it 55. So we can even add on this last note that it's equal to 1/2 the measure of the whole thing, which was ABC. And that might help us in solving it later on.